Okay, well, why is it so small on the screen? Anyways, so today I'd like to talk about vertex removal in approximate nearest neighbor search graph, or ANNS graphs. So here is kind of the overview of the presentation. So first I'll kind of explain the motivation behind this entire project, and then I'll go through a few algorithms that already exist. And then I'll show a few results from my experiments. And then finally, I'll kind of briefly mention what I plan to do in next term. So first, let's start with, also a disclaimer. In the context of my project, vertex, point, and vector refers to the same thing. So I thought I should probably mention that just in case I get any of them mixed up. Anyways, so let's start with similarity search. So by itself, similarity search is essentially about finding similar objects. So an example of it might be, or at least in computer science, might be recommendation systems, information retrieval systems, and search engine. To give a little bit more concrete example, let's say that I just watched a documentary called Inside the Mind of a Cat, and I really loved it, and I told Netflix that I loved it, you know. And then Netflix wants to keep me on their website or on their service. So they probably want to recommend me something that it knows that I like. So it has two choices. It can show me another documentary about cat people, or it can show me an anime about killing monsters. So most likely, it's going to recommend me something that is similar to what I just watched and really liked. To give a more concrete example, before I get into this example, let me use another one first. So let's say I have, so this example has a data set and a query point. So a real world example might be, I give you my pencil case, and inside of it, I have a lot of pens and pencils, and then I also tell you that here's a query point. Please find me, let's say, 2 items from this pencil case that looks like it. So far, I've told you that the object that I want is things inside pencil case, so mostly stationary, and the similarity function or distance function is their looks. So you might go through my pencil case and then pull out this thing that looks kind of similar. Like they look kind of close. And then another one might be this one, this blue pen. And although they don't look very similar because the color is different, if you compare it to things that are inside of my pencil case, you can kind of tell that these things are more closely related than the rest because these are light colored and stuff. So in terms of mathematics, we usually refer to objects as vectors and the similarity measure as the distance function. The most popular one that I've seen is L2 Euclidean space, or whatever the actual term is. And the problem so similarity search is usually formulated as a problem called k-nearest neighbor search. Essentially, I give you a data set and a query point, so the blue points and the one orange dot, and then you will give me the green points, which are closest to the query point from the blue points. A bit formally, let's skip that one. So the formal definition is there's given a point set P and a query point Q and a distance function delta. We want to find a set K such that set K has K members inside of it, such that everything inside of the set K is closer to the query point than everything outside of set K. So I've kind of separated the different sets down here. So this is the point set, this is the query point, and this is the set K. And I think I can probably easily convince you that things in here are closer than things in here, right? So that's the main idea for k-nearest neighbor search. So the next thing is, why do we bother with graph data structure for nearest neighbor search? So big and high dimensional data sets have become a lot more common, something along the lines of a vectors of 100 or more dimensions. And exact solutions are really expensive. And when it comes to other methods, such as tree-based or hash-based solutions, it usually breaks down when dimensions get really high because of curves of dimensionality. So in general, graphs tend to work better because tree and hash-based solutions usually do some kind of segmentation, which is very rigid, and it relies on points being close together. But in high dimensions, points are usually sparser, so it doesn't work as well. And then the final part is, why do we care about removal? So existing algorithms that I'll show later on are insert only, meaning that you can put a new point inside of it. You can mark existing points as deleted, but you can't really remove that point outside of the index. So if data becomes stale, it's still kind of in there. And the challenge that comes with removal in general is that if you just pluck a point out, what could happen is your graph becomes disconnected, and that would cause the quality and performance of your ANNS applications to be worse. And that's kind of the goal or the motivation behind this project. So the goal, at least for now, is to design a data structure that supports efficient vertex removal, or at least that was the initial goal. But the ultimate goal of this entire project is to design an efficient data structure for ANNS application in the sliding window setting. So essentially, you keep n most recent points, and then if a new point comes in, you throw the oldest one out, or something along those lines. So that's for the motivations. Now I'll go through a few algorithms that I've seen in literature. So in general, graph-based ANNS algorithms have two main phases. So we have index construction, or building the graph itself, and doing the search on the graph. The search on the graph is pretty similar across all algorithms, where it just do a greedy search on the graph, and then they modify greedy search to fit that data structure itself. So let's go through the search algorithm itself. This is the algorithm. We'll not spend a lot of time here, but in general, you kind of keep a collection of points. So here I call it L. And then you go through the graph and kind of greedily choose the closest point among the neighbors, move to that point, and then keep going until you get close, very close to your query point. To better visualize this, I'm not sure if the color is very clear, but you usually start with some starting point. So in this case, I made it red, and your query point is Q. So the algorithm, what it usually does is it adds the neighbor of your starting point or current point, and then put it into the queue, finds the closest point to the query point among that work queue. So this is the green here is your work queue. I'm not sure if it's very clear. And then you find the closest point, which is this one, and then you repeat that process until eventually you can't really get any closer to your query point. And then eventually this is what you return. So you return the closest nearest neighbors, which is in green, and then the path that you took from the starting point to the nearest neighbor, which is in red here. Any questions so far? Okay, so in terms of the existing algorithms, the search for each index is basically a modification of this. But it usually has like its own twist according to how the index is built. And then now let's move on to the index construction algorithm. So for most algorithms, this is kind of how they build their index. You start with, you go through the points that you want to put into the graph. You do greedy search, like I just showed before, and then you cut out repetitive edges. And the idea behind cutting out repetitive edges is something kind of like this. So let's say my starting point is here, and then my query point is here. In order for me to get from my starting point to query, I might have to visit these nodes or these vertices. But the thing is, when we want to connect the starting point to the query point, it might not be very useful to keep like these 2 points. So in this step in line 4 where it says cut out repetitive edges, it refers to if 2 vertices are too close to each other, you only connect to one of them. So in the end, you will end up with a path from starting point to your query or your new point that you're inserting into the graph, kind of like this, instead of going through all of them, which would take more time. And these are the 2 best performing so far algorithms. So we have hierarchical, navigable, small world graph, and discant graph. I asked one of my friends how to pronounce this word, and he said handsaw, so I'm going to refer to it as handsaw from now on. So the idea behind handsaw is you keep every single point in layer 0, and then you use some probability to promote and clone it up to higher levels in order to make your graph connected. A similar idea can be seen in discant graph, but instead of having multiple layers, it kind of squashes everything into the same layer. So between the 2 algorithms, the similarity is that it expresses some kind of long edges and short edges relationship. So in handsaw, its long edges is in the higher level. So you can imagine that in the highest level, there aren't a lot of points and they are kind of far from each other. So you have these long edges that you can travel to really quickly. And then once you're done with the current level, you go down to the next level. And then you can kind of get closer and closer to your actual query point. And that's kind of how they achieve their performance. And discant tries to achieve something similar, but they try to do it within one layer. So the differences, apart from being multi-layer and one layer, is that handsaw is undirected and discant is directed. The reason I mentioned this will come up later. And the last difference is their pruning criteria, or the criteria of how they cut out, the criteria for how they define repetitive edges. For the example that I showed here is how discant does its pruning. So essentially, it tries to make sure that there aren't a lot of vertices that are close to each other in the path from starting to query. For handsaw, it's a little bit different, where you kind of only keep points that are closest to your query point. So something along the lines of you only pick points that are in this radius from your path from start to query. And why should we care about handsaw and discant? Because when we consider removal in ANNS graph, we want to make sure that it doesn't degrade the quality of existing algorithms. So I thought, okay, starting from some existing data structures might be a better idea to kind of build the removal process into it, rather than designing a whole new data structure by itself. And handsaw and discant are the only 2 promising ones. So one of the problems that came up is that in a lot of literature, handsaw is really popular, but discant, although it seems to perform really well, it's not really mentioned in a lot of papers. Like when papers refer to ANNS application, they usually refer to handsaw, and discant is kind of ignored. So, but from my personal experience, I feel like discant might perform better because does everything in one layer while also having similar structure. So at least, even if everything is similar, you shouldn't need, you should need less memory to store it, to store the index or the graph itself. So I came up with an experiment. So the quality measures that I use for this experiment are build time, search latency, index size in memory, and recall. And recall is essentially how, you can think of it as how many points in the output of an ANNS algorithm is actually in the true nearest neighbor. So basically how accurate an ANNS algorithm is compared to an exact solution. And here, the experimental setup, I just stole a few implementations from GitHub. For handsaw, I used the implementation from FICE, which is implemented by Facebook AI, similarity search. And for Discan, I use Discan Pi, which is implemented by the authors of Discan themselves. And for the data set, I used SIFT1M, which is a million vectors of 128 dimension, and GIST1M, which is basically SIFT1M, but instead of 128 dimensions, it has 960 dimensions instead. So here are the results. For SIFT1M, you can kind of see that the build time for handsaw is higher, at least for this parameter. And the search is about the same. The size of the index is larger, and the recall is a little bit lower. But if you change the parameters to be roughly the same, Discan Pi would still win in terms of recall and index, but it takes longer to search, and it also takes longer to create the index. The other result is for GIST1M. So for handsaw, with equal build time, handsaw is able to get more accurate results, basically. The index size is going to be big either way because of the size of the data set. And the search time for handsaw is also faster. But if you are willing to sacrifice build time, you are also able to get higher recall or higher accuracy as well. So at the end of the day, it's a question of which trade-off are you willing to make. So Discan generally dominates handsaw in easier data sets, but when your data set become harder, especially with higher dimensions, handsaw seems to be more robust. And that's kind of the conclusion that I got from my experiments. And that's mostly it. Here are a few future plans. So I would need to come up with removal algorithms for both and implement them and benchmark them and then pick the good ones and then try to parallelize them and then benchmark them again and hopefully graduate in time. And that's it for my presentation. Oh, wait, one more thing, sorry. I want to note something that Ajahn Kanat also mentioned to me is that the way of supporting sliding window, removal is not the only way of supporting sliding window settings. There are other ways, but at least for now, I want to kind of look into removal and then look into other techniques later if I have time. So that's it for real this time.